Yes, very good morning to all of you. So far in earlier classes, we discussed about the single phase semi-control converter pad as well as single phase fully controlled converter pad, DC separately excited motor pad, and single phase semi-control converter, single phase fully controlled converter pad, DC series motor drives, and also the problems belongs to the DC separately excited drive as well as series motor drives are completed so far. So now in this class onwards, we are going to be discuss about the three-phase drives, three-phase control drives. So now I'm sharing my presentation here. Yes, yes, students. So after completion of the single-phase drives, now in this class onwards, we are going to be discuss about the three-phase control drives. So in general, we have a well awareness on what is the difference between single phase drives as well as the three phase drives. So single phase supply generally used for domestic purpose, and three phase supply are generally used for the industrial applications. Yes. So when high power requirements, high output power requirements is required, definitely we will approach for the three-phase fully control, the three-phase control drives. Yes. So let us see here. Three-phase drives are used for high power applications up to multi-megawatt power levels. Up to multi-megawatt power levels. For example, in market you can go. In market you can observe different ratings of the motors are available for us. Yes. So why we approach for the three-phase drives in the sense where more work done is required, more power is required, is more torque is required. So we can approach for the three-phase control. So especially these drives are used for high power applications up to multi-megawatt range levels. Yes. So when compared with the single phase drives, what are the benefits of the three-phase drives? Let us have a discussion here. So generally, for single phase supply, every 180 degrees there is a pulse. So a sinusoidal single phase supply you are taking, every 180 degrees there will be a pulse change. But whereas you can observe in the three-phase system, every 60 degrees there is a pulse. So as per general awareness, as the pulse number increases, the ripple content, the harmonic content, all are decreases. Yes. So in case of the three-phase drives, the pulse number is increasing, resulting the ripple content in the output is very small. So ripple content is very small, so that the ripple frequency is very high, and the filtering requirement is less. So filtering in the sense, the low pass filter, high pass filter, all the filters are used to minimize the harmonics or ripples or distortions. So these made with the capacitors and inductors. So the cost of the filters are very, very high. So as the filtering requirement is reduced, so that this drive is more economical. Yes, and that too, due to increased pulse number, this drive most of the time operates in continuous conduction mode. Yes. So these drives are better compared to single phase drive because the output ripple is very small. Yes. So the ripple frequency is large and filtering requirement is less. So moreover, in three phase drives, armature current is mostly continuous and performance is better than single phase drives. Yes. Three phase is so three-phase semi-control converter pad DC separately excited. Yes. So before going to start the three-phase drives, so we should have a 2 marks question on behalf of this theoretical discussion. So that is mention the advantages of three-phase drives over the single-phase drives. Yes. So what are the advantages of a three-phase drives compared to single-phase drive? So three-phase drives are used for high power applications, high power to multi-megawatt power levels, and The ripple in the as the pulse number increases, the ripple content is very small and the ripple frequency is very high, so that the filtering requirements are very less. And most of the time, this drive operates in the continuous current operation. So at this points, you have to be describe the differences between the single phase semi-control converter drive as well as three phase fully controlled single phase drives as well as three phase drives. So let us start with the first drive in the three phase, that is the three phase semi-controlled converter fed DC separately excited drive. Yes. So here supply is a three phase, converter is a semi-converter, and supply is a DC separate drive is a DC separately excited motor. Yes. So let us see the drive circuit diagram and the coordinate operation of a three phase semi-controlled converter fed DC separately excited motor as shown. Yes. So semi-controlled in the sense it is a single coordinate and it is useful up to the applications 15 to 150 HP. Yes. So you see here it is a single coordinate and applications in the range of 15 to 150 HP. It is a single coordinate converter. All the semi-controlled converters are single coordinate converters and the applications in the range of 15 to 150 HP horsepower is capable. Yes. So the field is fed from a control converter if field control is necessary. Otherwise, it is fed from a uncontrolled converter. Yes. So let us go for the circuit diagram. Yes. So three phase semi-controlled converter fed DC separately excited drive. Three phase semi-controlled converter fed DC separately excited. So let us see the circuit diagram. So the supply is a three phase VA, EB, VC. VA, VB, VC is the three phase supply. And the converter is a semi-controlled converter. Three phase semi-controlled converter. Three phase in the sense it has a three legs, each leg having a two switches. Totally 6 switches are there. Out of 6 switches, 3 switches are control switches T1, T2, T3, and 3 switches are uncontrolled switches such as D1, D2, D3. Yes. So AC supply is converting into DC supply with help of a three-phase semi-controlled converter, and the DC supply is feeding the armature of the drive between the terminals A1 and A2. And it is a DC separately excited drive. The excitation is externally supplied. The excitation is externally supplied. So the excitation is externally supplied with a converter. So we have so many advantages when the supply is feeding through a converter than without converter. So what is the advantages here? As long as the supply is feeding through a converter, there is a possibility of changing the field current. Changing the field current will change the speed of the system. So there are two converters. One is a three-phase semi-control converter for controlling the voltage across the armature, and this is helpful for changing the speed of the motor through armature control method. And other one is the field converter, which is useful to change the field current. So that field current change will change the speed of the motor above the rated speeds. Yes. So armature converter is useful for below rated speeds. Field converter is useful for above rated speeds. Yes. So this is the drive circuit. This is a drive circuit. And this one is the coordinate operation. This one is a coordinate operation. Why? Because all the semi-control converters are single coordinate converters. Yes. So as long as the drive is operating, the power transferred from source to the load only. Load to the source, there is no possibility because diodes does not support because it is a semi-control converter. So therefore, as long as power transferred from source to the load, the supply, the average output voltage, average output current, both are positive, so that the power developed is positive, which is in the first coordinate, that is the forward motoring. Yes. So the VA versus IA in first coordinate. So this should be the forward motoring. Yes. So this diagram represents the three-phase semi-control converter fed DC separately excited motor. Yes. So after heading, and you have after diagram and coordinate operation, you have to be describe the circuit. Yes. So the circuit consisting of is so the three-phase semi-control converter fed DC separately excited motor and its coordinate operation as shown. Yes. So the armature is feeding by a three-phase semi-control converter, which is consisting of 6 switches. Out of 6, 3 switches are upper switches are control switches and lower switches are uncontrolled switches. Yes. So the upper switches are T1, T2, T3 and lower switches are D1, D2, D3, which is feeding the armature. So similarly, the field is fed from a control converter if field control is necessary. Otherwise, it is feeding it through a uncontrolled converter so that the field control is not provided. Yes. So correspondingly, the coordinate operation in the first quadrant dash shown. Yes. So this diagram describes the three-phase semi-control converter for DC separately excited drive. Yes. Let us go after the description of the circuit. Let's go for the principle of operation in continuous conduction mode. Right. So principle of operation generally discussed in 2 modes of operation. One is the continuous conduction mode. Another one is discontinuous conduction mode. Discontinuous conduction mode is no need for us. Why? Because it is not included in our syllabus. So only you should concentrate on the continuous conduction mode. Yes. So the principle of operation in continuous conduction mode always should explain in the support of the waveforms only. So let us have a waveforms here. Yes. So let us see the waveforms here. Yes. So once you understand the principle of operation through these waveforms, then the operation is very simple for us. Yes. So the three-phase supply VS. Yes. So you see here, this is the phase A, phase B, and phase C. So these are continuously rotating. Yes. This is the simple representation of the three-phase AC supply. Three-phase AC supply. Okay. So now in this, you have to be identify this source waveform is very, very important to analyze the output voltage waveform as well as the current waveform. So how it is in the sense, once it has a reference, based upon this reference, you can follow for any firing angle, whatever may be the asked firing angle, based upon that firing angle, you can proceed. Yes. So VS. So you see here how the phase A is to be represented, how the phase B is to be represented, and how the phase C is to be represented. Yes. So every pulse has, in this three-phase supply, every pulse is existing in 60 degrees duration. 0, 60, 120, 180. Yes. So 240, 300, 360 like this. It is keep on increasing. So you have to be recognized this the phase VA, EB, AC. Okay. So that means that every 180 degrees there is a 3 pulse. Therefore, the ripple frequency is very high. And the filtering requirements also very less. So, and also most of the time this drive operates in the continuous conduction. Okay. So now after drawing the neat source waveform, you can draw the average output voltage and current waveforms for any firing angle. For example, I am taking alpha is equal to 90 degrees. Alpha is equal to average output voltage for alpha is equal to 90 degrees. So alpha is equal to 90 degrees in the sense the omega t will commence at the 5/6 plus alpha, which is equal to 120 degrees. 5/6 plus alpha. Alpha is 90, 5/6 is 30, which is equal to 120 degrees. Yes. So 120 degrees it will be commenced. At 120 degrees it will become. Why? Because why this 5/6 has? Yes. So you can observe in the waveforms. So at any instant of the time you can observe one waveform is going, one phase is going to off, another phase is coming to in, on. Yes. One is outgoing, another one is incoming. That means that, so one thyristor goes to off state, another thyristor will come into on state. So like that, at every instant of the time, any one thyristor will take the responsibility of the transferring power from source to the load. Yes. So during this, there may be a span of 30 degrees. It will be overlapping from one phase to the other phase. So this may leads to the firing angle VA. The average output voltage for firing angle alpha is equal to 90 degrees is equal to 5/6 plus 90. It is commenced at 120 degrees. Commenced at 120 degrees. Yes. So I think this phenomena already covered in the power electronics. So just anyhow, due to this overlap is to be happen because of the source inductance. Yes. So for 3 pulse, you have to be considered this is 30 degrees. For 6 pulse, you have to be considered it is a 60 degrees, 5 by 3. 5 by 3. 3 pulse, you have to consider it as a 5 by 6. For 6 pulse, you have to consider it as a 5 by 3. 5 by 3 plus 90 is equal to 120 degrees. Yes. So you observe here at any instant of the time, one switch is in upper half, another switch is in lower half are going to be conduct. Yes. So let us see here. You see here, initially the phase A is connected to first link. Phase A is connected to first link, and phase B is connected to second link. Phase C is connected to third link. Yes. So for example, phase A, you are starting from the phase A. So you are giving the triggering pulse for the thyristor T. Triggering pulse for the thyristor T. So thyristor T1 is turn on. Turn on in the sense it acts as a short circuit. So that the power transferred from phase A to T1 to armature of the motor, and then comes here, and it is thinking there is no provision to conduct in the D1 because so there is no possibility to conduct both switches in the same leg is functioning simultaneously. If it is functioning simultaneously, it becomes a short circuit, therefore the entire circuit may be destroyed. So no same devices are functioning. Yes? So that's why it can prepare the which for this either D3, D2. So in this instant of the time, which is highest negative potential, we can observe here. You can observe in the waveforms. So here, suppose if alpha is equal to 90 degrees, you are in triggering the thyristor T1 at 120 degrees instant. So what is the highest negative potential? This one. This one is the phase C. Phase C. Yes. So phase C is the highest negative potential. So which is the switch connected to the phase C? That is the D3. D3 will come into conduction. Okay. So you can observe here. In upper half, thyristor T1. Lower half, the D3 is coming to action. Yes. So it commenced at 120 degrees so that the average output voltage will be appear like that. And this will be continue up to this one. Up to this one, this is hardly 180 plus 30, 210 degrees. This is omega T4. Omega T4. At 210 degrees, what will happen? The phase C is going to off. Phase C is going to be off, and phase A is the supply voltage is reverse, resulting the thyristor is the phase A supply voltage is reverse at this particular instant. So supply voltage is reverse in the sense the thyristor T1 is automatically turns off, so that no thyristor is in active condition. Therefore, there is no power transfer from source to the load. So at that time, already the motor is connected to some active load and is in running condition, so that the motor pre-wheels through the pre-wheeling diode. You see here, no switch is in conduction mode in the sense the motor is pre-wheels through the pre-wheeling diode. Therefore, the motor terminals are shorted through the pre-wheeling diode. Motor terminals are shorted through the pre-wheeling diode, resulting the voltage across the armature is equal to 0. Yes. So you can observe from 210 to 240, 210 to 240, where the freewheeling diode will be come into action. So the motor current is circulates through the freewheeling diode. The motor current is circulates through the freewheeling. Yes. So from 120 to 210, the thyristor T1 diode D3 will conducting, where the VI is equal to Vs, and at omega at 210 degrees, the thyristor T1 is to be turns up automatically due to natural commutation, the reverse voltage applied across the T1. So it should go to off state. And then over a 30 periods or 30 degrees of the span, the prevailing diode will become into conduction, and this makes the continuous current. This makes the continuous current. Is so when T1 D3 operating, the current passing from source to the load, and during the prevailing diode also, the motor current is continuously passing through the prevailing diode. After that, again at 240 degrees, the T2 will be functioning. T2 will be functioning, and which is the highest negative potential? Phase A is the highest negative potential. So phase A is connected to D1 diode. So T2 D1 is functioning. So this process will be keep on continuing. Yes. So this will conduct for 90 degrees. Yes. After that, pi by 6 plus 90 degrees. This will conduct pi by 6 plus 90 degrees. And after that, the T3 will be come into action, and T3 is to be triggered at this one and 360 degrees. So D2 will be come into action. So this will make the conduction continuous. Yes. So this is the way to operate the switches T1, D3. Next, T2, D1. Next, T3, D2. Like that, this operation is continuously repeating. So the average output voltage for alpha is equal to 90 degrees, and corresponding current waveforms also observed in this way. Yes. So once this is the waveform observation, once you understand the waveform observation, you can describe the operation here. So the conduction periods of the diodes and thyristors as shown. The conduction periods of the diodes and thyristors as shown. The diodes D1, D2, and D3 conducting during the interval. The diodes D1, D2, D3 conducting during the intervals T4 to T6, T6 to T8, and T2 to T4. Yes. So already we discussed about D3. D3 will be functioning from T2 to T4. Yes. So after that, the D1 will come into action. D1 is T4 to T6, and D2 is T6 to T8. Similarly, the thyristor T1, T2, T3 are conducting during the intervals. So thyristor T1 conducting T3 to T5. Sorry, the thyristor T1 is conducting the interval T1 to T3. That means that the same thyristor will be functioning for T1 and T3, and T2 thyristor is functioning for T3 and T5, and T3 thyristor is functioning for T5 and T7. Yes. So these intervals for easy recognizing the intervals. So upper half is diodes, lower half is thyristors. Yes. So, and the thyristors T1, D3 conducting during the interval pi by 6 less than or equal to omega t less than or equal to omega T4. This is the omega T4. It is hardly 210 degrees. 210 degrees. So during this, the motor terminal voltage is directly connected to the phase voltage V. The average output voltage is directly connected to phase A. So therefore, so during this period, VA is equal to the voltage across the armature is equal to VA minus VC. That is the VAC. VA minus VC. That is the VAC. And then at omega T4, the VA is equal to 0 because of the prevailing diode. So this is the operation we know clearly. Yes. Then derive the average output voltage. So for this, the supply voltage has to be defined here. Let the supply voltage is defined as VAN is equal to Vm sin omega t. VBN is equal to Vm sin omega t minus 120. VCN is equal to Vm sin omega t plus 120. So minus 240 or plus 120. Yes. So therefore, the average terminal voltage can be expressed as when the drive is operating in continuous conduction mode. Yes. So this is the value of average output voltage. Yes. So VA is equal to 3 by 2 pi, 3 pulse. Yes. So 3 by 2 pi integral pi by 6 plus alpha to pi by 6 plus alpha plus 2 pi by 3. So at any instant of the thyristor T1 is responsible for 120 degrees conduction in support of the D1 and D3. Yes. So like that, one thyristor sharing the conduction with two diodes. Yes. So VA is equal to 3 by 2 pi integral pi by 6 plus alpha to pi by 6 plus alpha plus 2 pi by 3. So every thyristor is responsible for 120 degrees conduction. So that the thyristors are responsible for 360 degrees conduction. After that, the process will be repeated. Yes. What is the VAC? VAC is VA minus VC. VAN minus VCN. VAN is the VM sin omega t. ECN is the VM sin omega t minus 240 or plus 120. Yes. So VAC is equal to VAN minus VC. So for solving what is the value of VAN minus VCN? So VAN already we defined that VM sin omega t. This one is VM sin omega t plus 120. Yes. So which is equal to sin omega t minus. So here sin omega t plus 120. Sin A plus B can be termed as sin A cos B plus cos A sin B. So in this manner, we can solve this one. Finally, VAN minus VCN have an value of square root of root 3 into VM sin omega t minus pi by 6. So how this expression is getting? So it will for this derivation you have to be is. So therefore you substitute here, and 3 by 2 pi integral pi by 6 plus alpha. So pi by 6 plus 2 pi by 3 become 150. So root 3 into VM sin omega t minus pi by 6 into d omega t. So how this value is coming in the sense, this is the evidence is. And this is also equal to, you take root 3 and VM both are constants, you take print. So 3 root 3 VM by 2 pi integral pi by 6 plus alpha 2, where the thyristors making conduction 0 to 10 degrees. 210 degrees. That is the 150 plus 60 is. So sin omega t minus pi by 6 d omega, which is equal to 3 root 3 VM by 2 pi. 3 root 3 VM by 2 pi. So sin omega t become minus cos omega t minus pi by 6. The limits are pi by 6 plus alpha to 210. So you have to solve this one. 3 root 3 VM by 2 pi. So minus 210 minus 30, that is the minus 180 plus cos alpha. Here pi by 6 will cancel. So finally cos 180 is equal to minus 1, minus of minus 6 place. So VA is equal to 3 root 3 VM by 2 pi into 1 plus cos alpha. Yes. So this is the average output voltage. This is the average output voltage. And then from this, the average speed equation is to be getting T is equal to K pi Ia, EB is equal to, this is the separately excited motor, the constant flux motion. Torque is directly proportional to pi into Ia, but remove the proportionality constant, K into pi into I. EB is equal to K pi omega, this is also known equation, and EB is equal to EB plus Ia. From all these equations, the average speed can be getting with the help of this formula. Yes. So omega m is equal to 3 root 3 Vm. As per this expression, you can obtain this omega. 3 root 3 Vm by 2 pi 1 plus cos alpha divided by K pi minus T into R by K pi whole square. This is the speed equation, average speed equation of a 3-phase semi-control converter paired DC separately excited. And once the speed equation is getting in terms of the torque, so that the speed torque characteristics can be achieved as like this. Yes. So speed torque characteristics, already so many times we discussed, the speed torque characteristics are achieved when achieved from the no load space, which are to be obtained with the help of the IA is substituted in the above equation. IA is substituted in the above equation. This term here has 0. This term has 0. So therefore, U should be greater than or equal to Vm when alpha less than 90, and V should be greater than or equal to Vm sin omega t when alpha greater than pi by 2 or 90. Yes. So the characteristics you can observe. That alpha is equal to 0. What is the speed? What is the speed? Yes. These are the no load speeds. Okay. So speed versus torque. So this characteristics also similar to that of the first single phase single phase semi control converter pad DC separately excited, right? So the coordinates completely occupied in the first coordinate from alpha to 180 degrees. So there is no second coordinate. So only it occupies in the first coordinate. So this is this dotted line describes the boundary between continuous and discontinuous conduction modes, which is separated by separated by the critical speed. Yes, these waveforms are discontinuous operation and these waveforms are continuous operation. Yes, so speed torque curves of a three-phase semi-control converter pad DC excited mode. And there is a discussion here why this drive operates in the first coordinate only. The circuit is useful to why this drive should not operate in the fourth coordinate. So it will help the VA versus alpha curve, VA versus alpha curve. Yes. So if you substitute VM is equal, alpha is equal to 0, it is the 3 root 3 VM by pi is the maximum magnitude available. And there onwards, you can vary from 0 to 180 degrees. The average output voltage does not change. It is always positive. It is always positive. Yes. So this is the evidence for us so that it will occupied in the first part. Similarly, in the braking operation, the semi-control converter does not change the polarities. It is always plus and minus. And the supply voltage change, the back EMF change in back EMF will reverse the speed so that the polarities of armature has to be changed like this. The polarities are changed like this, therefore the motor acts as a generator and it transfers the power from load to the source. But the converter, three-phase semi-control converter does not support the reversal of power flow. Therefore, the developed energy is to be dissipated within the armature itself. The type of braking is known as the reverse voltage braking or plucking. Yes. So the output voltage cannot be reversed when coupled to an active load. Due to reversing back EMF, the machine works as a generator producing braking torque. So since control rectifier cannot be transferred to the source, then it is observed in the armature circuit resistance known as the reverse voltage or plucking. Yes. So this is about the three-phase semi-control converter pad DC separately excited motor, right? Yes. So here we are describing each and every function, including circuit operation and the speed torque characteristics and VA versus alpha curve motoring and braking operation. And finally, you conclude that. So this drive has so many drawbacks. Yes, it is capable of allowing a single coordinate, and during the braking, there is no provision for transferring energy to the source, resulting the entire amount of energy is dissipated within the armature itself, so that there may be a provision for overheat the armature so that the lifetime of the armature is reduced, the converter may be spoiled. So to avoid all these drawbacks, we are going to approach for the three-phase fully controlled converter. So that drive has an ability to transfer the power from source to the load as well as the load to the source. So we can explain. We will explain about the three-phase fully controlled converter in the next video. Thank you. Thank you, Ananda.